and my talk is titled 5 Levels of High Availability from Multi-Instance to Hybrid Cloud. I'm speaking to you from Krakow, from my apartment, as we all do everything from home, so I'm also talking now from home, from Poland. Before I start, let me tell you a few words about myself. So I'm a cloud software engineer working at Hazelcast. Before I worked at Google and CERN, and I'm also an author of the book Continuous Delivery with Docker and Jenkins. From time to time, I do trainings and conference speaking, but on a daily basis, I'm coding. So I'm a developer. Also, a few words about Hazelcast. You might have heard about Hazelcast. Hazelcast is a distributed company, and it is distributed in 2 meanings. So one meaning is it is distributed because we produce distributed software. Our products are Hazelcast, which is called in-memory data grid, Hazelcast Jet, which is a library for stream processing, and Hazelcast Cloud is Hazelcast put as a service in the cloud. But there is also a second meaning of the distributed company, and the second meaning is we all work remotely, meaning this is a company founded as a distributed company, and even before the coronavirus, we all work remotely. We meet like 4 times a year, and apart from that, every synchronization between the teams is done remotely. Our agenda for today is pretty simple. So there will be a short introduction about high availability in general, and then I will walk through all possible levels that you can use in your system. And while I'll be speaking, I would like you to focus on 2 things. First thing is, which high availability level do you use in your system? Because this list is complete, so you must use one of them. And the second question is, would it be simple for my architecture, for my system, to upgrade to a higher level? So taking my system, taking your system, would it be simple to upgrade it? And with this question, I invite you to listen to this talk. So a short introduction about high availability. So in the center of every system, there is a service. Now we sometimes call it microservice. Sometimes we call it microservice, even though it's a very big in terms of the code. But it doesn't matter if it's a microservice, macroservice, or even like serverless Lambda. So what matters in this service part, it is that it is stateless. And the stateless things are easy. Just imagine that the whole world, your whole system is just a bunch of stateless services. Like, let's say, a calculator service that adds 2 numbers. Your life will be super easy because you can deploy it anywhere you want. You can deploy it on your laptop. It works the same as if you deploy it on AWS. So there is no problem with deployment, high availability, nothing. But that is not how our IT world look like. Because in our IT world, this stateless simple thing is always connected to some stateful things like data store or a queue or some external services or internal services, basically some other services. And this data thing, this stateful thing, this is the problem in terms of high availability. And that is why in this whole talk, I will always give you the whole architecture for all these levels. However, I will focus on the data part because the rest is just super simple. And when I will be focusing on the data part, I will give you the examples of Hazelcast, which is in-memory data grid. So it's stateful, it stores data. So with this short introduction, we are ready for the level 0, which means running everything on a single instance. How does it look like? So a diagram could be presented like this. So a request goes to our system, and now all the stateless part or the stateful part, this is all deployed on one machine. You can think of this as like a development environment. That is a good example. You may think like, but come on, what kind of YOLO software cowboys would use this system? This is insane. But remember that not everything in the software needs to be highly available. For example, an idempotent batch job, which you can repeat anytime you want. This is good as it is to run on a single instance. And running things on a single instance have some benefits. So I did a latency experiment. I ran Hazelcast and a service on my local machine, on my laptop, and measured the latency. So the result was like this. For 10,000 of entries, I got 80 milliseconds. For read-write of just a simple value read-write. So obviously it doesn't tell much. We will just compare this latency to the higher levels. But you can already see that the value is low. Latency is very good because it's way less than 1 millisecond per entry. So you can consider this good, which is what we expected. We didn't have like even the networking. We could run it even in one process. So what does single instance mean to you? So obviously there is no high availability, there is no scalability, but from the good sides you have low latency and the data is consistent. And the data is consistent. This is something we will somehow lose in the higher levels. So what's this part? But okay, you didn't join this talk to hear about like simple development environment. So let's go straight to the first really highly available system, running on multiple instances. Running on multiple instances means that if one machine is down, your system is still available. And a diagram could look something like this. So request goes now to load balancer, which load balances the traffic to our application services. And obviously application services are deployed on multiple machines, but that's easy. But also our data part needs to be deployed on multiple machines. If you look at this diagram, there is only one box that is like single on this diagram, and that is load balancer. However, we will not talk a lot about load balancer because this problem is kind of solved. You can use some DNS-based load balancing or use some very reliable load balancers available somewhere in the cloud. So we'll not focus on load balancer. We will not focus also on the application services because they are stateless. And as we said, that is the simple part. So we will focus on the data. So to make like the assumptions here clear. So we have two machines with two instances of the database. They are connected with a local network, which is fast and reliable. And as an example, you can have two EC2 instances or any cloud instances like GCP, virtual machine, or Azure. Usually this data, these machines, it's like a rack in a data store. This image is actually taken from the CERN when I used to work in Geneva. By the way, if you happen to be in Geneva, you can visit CERN, and it's super interesting. You can visit this for free. So if you come nearby by car or something, just go there. You can assign for a tour, and you can visit all these colliders and all the stuff. So it's amazing. But coming back to our example, so we have like we have two database instances deployed on two machines, and we need to basically copy the data from one to another just to keep them consistent. And to describe how it's done, I need to tell you a short story about data replication, because that is the problems we try to solve right now. So you remember, like some time ago, like the databases were like equals the SQL databases, the relational databases like MySQL, Oracle, Postgres, and they all were focused like on this master-slave replication or active-passive. Active-passive means that we just write all the services use just one database, but everything is copied to some other database. Master-slave is basically the same, but you can read from the second one can be read only. But the idea is the same. You write to only one single instance of the database. Now, if this single this machine one, if it fails, we just do a failover. Application services, they switch to the second instance, and we obviously don't lose the data or anything. We make the failover. Obviously, we can connect this with the sharding if you want to strive for performance. No problem with that. Now, people thought like, because SQL databases were basically like quite complex, and with the emerge of the NoSQL databases, people thought we need something better. This look oldish, you know. You just use one instance, another one is not used; it's just used in case. So then there was the idea of clustering, and now all NoSQL databases, they use clustering. They don't use the simple master-slave replication. What does it mean, clustering? So clustering means that your services, they use all of the database instances at the same time. And each instance stores part of the data, also backups of other data. So they have knowledge. So even if the one machine is down, they can recover, they can restore from the partition backups the data. So it's very good in terms of the performance and also the resilience. To understand it a little better, let's step into the details of how Hazelcast works, because Hazelcast is, after all, is a key value database, which is an example of a NoSQL database. So it works like this. If we have 3 members, which are like three instances of the Hazelcast, and each of them stores part of the data. So we split all the data by some keys, put some keys in the partitions, and each instance of Hazelcast stores some of the data partitions. And now there is also data partition backups, and the rule here is that this backup is always stored on another member, and by default it's stored on one other member. That's why if any of the members, just one member fails at some point, the backups are promoted, and we don't experience any data loss, even though the whole data is stored in memory only. And that is like the whole idea of the clustering. That's basically how all these NoSQL databases work. Now the question, short question to you. Like, do you think this creating this backup, partition backup, or basically data backup, should it be done synchronously or asynchronously? In other words, should we favor consistency, then the backups are done synchronously, or should we favor latency, and then the backups are done asynchronously? And would it be different for master slave or the clustering, or is it the same? You can think for a moment, what if you were to put your money on one of the choice, is it synchronous or asynchronous? What would it do? And before I answer this question, I did another latency experiment. This time I've run Hazelcast on 3 machines, and I measured again the latency of read-write, and I measured this for the synchronous. So the backups are where they are synchronously, so we keep the consistency in the cluster, and the result was like this. So we had like 3,000 milliseconds per 10,000 entries. The number looks very big comparing to the level 0. However, if you think about it, it's still under 1 millisecond. So usually it's acceptable. That is why in Hazelcast, by default, obviously you can configure this, but by default, backups are created synchronously because we want to have this consistency inside the cluster. And this is what you will see in most clustering databases, that backups are usually done synchronously by default, at least. You can always tweak it, like configure this to favor latency, but latency is still good with the synchronous, so you can still have it right. Would it be the same for SQL databases and there's an active-passive for master-slave replication? Not necessarily. Actually, by default in MySQL, it's done asynchronously because it's actually a more complex operation. So they said it's just too heavy. We don't want to sacrifice the latency here. But obviously, you can configure this. So what does it mean? Like level 1, what does it mean for you? You can still have data consistency in your database, which is super good. Most tools supported. You can use some cloud-specific tools like AWS SQS supported. Actually, most cloud toolkits support high availability across multiple instances. And the setup is quite simple. Even if you're done on-premise, actually any database is relatively simple setup. From the downsides, if you are still bound to one region, so if you would like to access your system from multiple regions, then the latency from other regions would be high. Okay, let's move on to the level 2 multi-zone. Multi-zone means that if one availability zone is down, the system is still available. So that is how availability zone looks like. So there is like, this is like, I think this is the data center from Facebook. Usually, like the idea of the availability zone, it's usually a few data centers form one availability zone. But the idea is that each availability zone has a separate power supply. So in the case of the power failure, only one availability zone can be affected. And the same with all like resources, it needs to be autonomous in that sense. That is why you will see like, but on the other hand, you don't want them physically far away from each other. So usually there is like one city, and in different part of the city you have different availability zone, but they are autonomous. How the diagram for this look like? So again, request goes to the load balancer. Load balancer forwards the traffic to the application services. But this time, application services need to be located in different availability zones, and the same with our databases. So this diagram looks quite similar to what we've seen for multi-instance. So you may ask, is multi-zone deployment any different than multi-instance? And actually, I would say that no, but yes. Let me maybe first say why no. So I did another latency experiment, this time with Hazelcast instances running in multiple availability zones on AWS. The result was like this. Obviously, the latency is worse. It's a little higher, but it's not that much higher. It's not even twice higher than multi-instance. It's still under 1 millisecond, so it's still good. It's still good to run it as a consistent synchronous backup database. So in this sense, your deployment for multi-zone will be the same as multi-instance. However, I told you that there are some differences. And to understand the differences, I need to show you an example. So let's say we have like four instances of any database, and they are located in two high availability zones. For example, they can be located in, we can have two database instances in one zone on AWS and the 2 other database instances on other zone on AWS. Now, you remember this slide with Hazelcast, how it worked. So we had like data partitions, there were data partition backups, and the rule was that the partition backups always stored on another Hazelcast instance. Now, the rule is it should be always on another partition instance, but imagine what will happen like this in our scenario. So we can have one partition, and the backup of this partition is on another member, like member 2, but they are located in the same availability zone. So in the result, if zone 1 is down, then we lose the data, and that's obviously not something we would like to allow. So we thought how to solve it inside Hazelcast and how to approach this topic. And we came up with the feature called Zone Aware. So this is the configuration you would need to put in Hazelcast to tell, yes, run this cluster with the Zone Aware enabled. And we thought how to, because the high availability zone concept is a concept of the cloud provider. So it's different in AWS, in different GCP, different in Kubernetes, and so on. So we thought how to solve it. And we came up with the idea of plugins. So for each environment, you will have a dedicated plugin. And these plugins are also used for the discovery, by the way. But these plugins will use the API of the given platform to get the given availability zone, so that the Hazelcast instance is aware, okay, I'm in this zone, so now we can locate the backups in the way that the backup is always in another availability zone. That's why I say, there's not much difference, but there are some difference. So in terms of deployment, there is no difference, but make sure your data store supports zone aware feature, because this is not something you should take for granted. We spent some time implementing this, and not every data store has it. Short summary. Level 2, multi-zone. What does it mean to you? I would say it's now the top one choice, because you can still have data consistency and you are very high available, because it really doesn't happen at the cloud provider that two availability zones are down at the same time. Some cloud specific toolkit will support it, some no, you must check. And from the downsides, obviously your tool needs to support it, and the same as multi-instance, you are still bound to one region. So if your system is accessed from different region, you will get high latency. Okay, we covered the level 0, 1, 2. Let's move to multi-region, where the things are really getting interesting. So the multi-region means that if one region is down, the system is still available. That's the that will be the architecture. So you now have something called geo-load balancer, which can load balance the traffic, taking into consideration the location and the region. And then we will have the same environment like in the region 1 and region 2. Application services, no problem again, and the same databases, the database clusters actually, and the geo-replication in between of them. So to give the assumption, so now we'll have machines in at least 2 geographical regions, and the network now may be slow and unreliable. In multi-zone, cloud providers, they still have dedicated networking. Here, the network may be unreliable because in most cases, we will depend on the public routing. But you think about it, like what is the biggest problem in this whole like regions? So biggest problem is that they are just far away from each other, like physically. If you take like a Finland and Oregon, it's 10,000 kilometers between Oregon and Finland. So 10,000 kilometers, it means if we just calculate, we just take the speed of light and we calculate the speed of light in a vacuum and check the round trip time, it will give us 60 milliseconds just to light to go and back. And it was in the vacuum. In the fiber, it would take probably at least 3 times more. So we have 2000 milliseconds just for the signal to come. But you have all this routing in between and so on. So it's just, we'll never make it faster. And that's the biggest problem. And that is why we need something called geo-replication. Geo-replication is data replication between geographical regions. As simple as that. What is special about geo-replication? First thing, it's asynchronous. It just cannot be synchronous because it will be too slow. Latency will be too high because of this physical distance. Your data store must support it, which is not always the case. And you must be prepared for the data loss. And usually there are 2 modes for the geo-replication: active-passive and active-active. For the active-passive, you use only one of the database cluster, and you replicate your data to another cluster which is passive or read-only. And in this case, you have to be prepared for the data loss, because this the synchronization of the cluster it's done in an async manner. So just imagine that you wrote some data to your active cluster and it's suddenly down. So the event may be not received by the passive cluster, so you can lose the data. But you can still have some kind of consistency, meaning at least you have the same data here and there. For the active-active, it's even worse. Now you can read-write to both of the clusters, so you can obviously still lose the data. You have to be prepared for eventual consistency, but you also need to think about conflict resolution. Because just think, what will happen if you change the same data at the same time in 2 clusters? What should be the result? What should be this eventual consistency result? And there is no like one answer of how. There's no one answer how to make the conflict resolution. It will depend on your use case. So usually, like databases, they provide some, like Hazelcast also provides some policy that you can decide, okay, if I have a conflict, how to resolve it. And like basic policy can be first one wins or last one wins. Some databases, like I think Couchbase, they just store the tree of all the conflicts, and you from your application layer you are responsible for resolving these conflicts. But conflict resolution is a difficult problem. Just you can already imagine that. If you would like to configure geo-replication Hazelcast, that is how we do it. We call it one replication. Configuration is very simple. We just enable one replication and give you, okay, replicate to this target, to this IP. As simple as that. So we support like active passive and active active. But if you use some other tools, make sure this is not something, obviously not something you have to take for granted that your tool will support geo replication, because that is just a difficult feature. So not every tool supports it. Okay, you may ask the question, do I really need to lose the consistency? What if I would like to have my cluster consistent across multiple regions, whatever? So I did another latency experiment, and this time I've set up Hazelcast cluster across multiple regions. So something we should not do. So, but I wanted just to check what would be the latency if let's just do it. Like, let's do a synchronous consistent cluster across multiple regions. And the latency, you remember, like latency for multi-zone. So this time for multi-region was really way higher. So this is like latency that starts to be unacceptable. Your system will be terribly slow. That is why you don't use it. Obviously, like if we use like a Gen-replication, this is the same as multi-zone because we do replicate asynchronously. But you see, like you just cannot technically have a consistent cluster across multiple regions. And that is also the reason why to take, like, if you'd like to have a Kubernetes cluster across multiple regions, you can't do it. Everyone will tell you can't do it. You can have Kubernetes cluster across multiple zones, no problem with that. Even in GCP and GKE, you can just click, okay, I would like the multiple zones. That's fine. But you will never have like a Kubernetes cluster across multiple regions, because underneath Kubernetes uses an etcd data store, and it needs to synchronize with other instances of etcd, and it's just not possible across the regions. If you need like really strong consistency or like distributed transactions, then I encourage you to read like about new SQL databases like a Spanner or the open source version of Spanner, which is CockroachDB. They do some interesting things, like they have like very well synchronized clocks, and then they only wait for some time for the acknowledge event, but it can only reduce the time we wait. However, like there is still a trade-off between consistency and latency. Short summary about multi-region. So if you're multi-region, you are super highly available and you can achieve low latency if accessed from multiple regions. That's perfect. Sometimes it's possible to use some cloud-specific toolkits, like Spanner supports it, but AWS Elastic Cache, no. From the downside, you need to use Gen-replication, which is asynchronous, and you have to be prepared for eventual consistency and conflict resolution. Okay, let's move on. We went from the multi-region to multi-cloud. Multi-cloud means that if one cloud provider is down, your system is still available. So this will be the diagram. So we go to the global load balancer, which load balances the traffic across multiple cloud providers. And basically in each cloud provider, you have the same system. And the replication, obviously like a Gen-replication in between of them. So the assumption here is like, again, the network may be slow and unreliable, and machines can be in different geo-regions. So all this stuff we already mentioned in multi-region. You may say, like, what's different from multi-region? In terms of the deployment, it's similar. However, there are some differences. So first thing, you cannot use cloud-specific tools because they are different in different cloud providers. So you just cannot use there. You have like, you start, if you don't want to build heterogeneous environment but homogeneous, you need to deploy your own tools. Like, for example, for caching, you need to deploy Hazelcast. You cannot use Elastic Cache because it will not sync with GCP, because there is no Elastic Cache in GCP. You cannot use VPC peering across cloud providers, so you have to think more about security, and latency is worse. And obviously the cost, because you have to pay multiple cloud providers. So is kind of availability the only reason to choose multi-cloud? And you can already feel that probably no. There are some other reasons, like maybe the main reason even is to avoid vendor lock-in. So you start to design your system in a way that it works on multiple cloud providers, because then you have the choice. Your system is deployed on multiple cloud providers. You have the choice. You're also in better position with the cloud cost negotiation or optimization also, but also negotiation, because like the price for AWS paid by a big enterprise is not the same as the price you pay like personally. So you are better positioned to negotiate. Also, if you would like to achieve low latency from different cloud providers, then you deploy your system in multiple cloud providers. There's a lot about data protection regulation. You may have some non-technical, basically you may have some non-technical reasons for multi-cloud. And also if you build like heterogeneous environment, you might have use different cloud providers because you won't like to use specific technology. For example, you are interested in Google Spanner. That's why you take GCP into your system. Short summary. So level 4 multi-cloud. So you have no vendor lock-in. You're in better position in cloud cost negotiation, and you can achieve low latency if accessed from multiple clouds. Setup is way more complex because you cannot use tools from cloud portfolio. So basically you're on your own here. Last level is hybrid cloud. So hybrid cloud means that if all cloud providers are suddenly down, your system will still be available. You may ask, like, but really, like, is it possible that all cloud providers are down? And obviously, no, it's not possible. It will never happen. Even if one cloud provider is down, it's very unlikely. But all cloud providers, then probably the whole internet won't work. So there are other reasons for hybrid cloud. Main reason here will be like data regulations and requirements. So you may be forced by the business or by some regulations that you store the data of your customers on your servers in your building, like physical building. Also, another like good reason is that you have an on-premises environment and you are just moving to the cloud. That is why in this phase in between is hybrid cloud. And you for some reason, maybe also for cost reduction. So the diagram will be like this. So again, you have load balancer and load balancer traffic across multiple cloud providers, but also on your on-premises environment, on your own servers. And usually at this point, even in multi-cloud, you need some abstraction layer. So it may be like, nowadays it's mainly, I think Kubernetes won this war. And now this is orchestration you install everywhere, or some derivatives of Kubernetes like OpenShift or IBM Cloud. But other tools is like Pivotal Cloud Foundry, which is now renamed, bought by VMware Tanzu, or some older like Apache Mesos. But basically at this point, you need an abstraction layer because it's just impossible to manage. Summary of hybrid cloud. So what does it mean to you? You are completely no cloud lock-in. Latency can be low from any place you want because you just set up your servers anywhere you want, and latency can be low from there. But the setup is super complex, and it usually requires some additional layer, and it usually costs fortune. So usually it's for some big enterprises and banking industry.